All right, so in this video, we're going to talk about the equation of a plane. And so for an equation of a line, we said we need to start with two things. We need to start with a point and a direction vector. For a plane, we're going to need two things as well. A point being one of them, but no longer a direction vector, but a normal vector. And so a normal vector would be one that's perpendicular to the plane. So I'll go ahead and start with a picture here. We'll draw this guy here and we'll call this a plane. All right, and so then I'm going to go ahead and pick a point. Maybe we'll call this P naught, which is X naught, Y naught, and Z naught. And embedded in this plane, we can have a line. So embedded in the plane, we can have a line. And so maybe I'll call this guy here P of X, Y, Z. And so now we've got embedded in the plane is going to be now a normal vector coming out of that plane. So if I sketch that right here, this will be our normal vector. It's going to be perpendicular. And I'll go ahead and label that N being A, B, and C. So we've got our point, once again, P naught is X naught, Y naught, and Z naught. And we've got now N being our normal vector, A, B, and C. So one of the things that I'm going to use again is the fact that since I have this embedded line, I can construct a vector in component form, but with these 2 points. And so maybe just off to the side, so you can recall from the last video, P naught P ended up being X minus X naught, Y minus Y naught, and Z minus Z naught. Now, to put the rest of this together, we're actually going to take advantage of something we learned in a previous section. We know that if we take two vectors, we take vector N and we take vector P naught P, and we dot them, if we dot them, because they're perpendicular, the dot product should equal 0. And that's 0 the scalar, not 0 the vector. So I'm going to take N dot P naught P and set that equal to 0. Well, our N was A, B, C. P naught P was X minus X naught, Y minus Y naught, and Z minus Z naught. And that should equal 0. And again, that's 0 scalar, not 0 vector, because as we dot these things, we are not coming up with a vector. So we're going to have A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught, all equaling 0. So A times X minus X naught plus B Y minus Y naught plus C Z minus Z naught equals 0. Now, this, of course, could be simplified down to any number of formats. I kind of like the way this one looks for the same reasons as the equations of parametric lines. If you look at it like this, immediately out in front, those coefficients, A, B, and C, those are the components of the normal vector, and the X naught, Y naught, and Z naught, those are going to be the points. So you can construct and deconstruct these planes into the points and normal very, very quickly in this form. Now, that's not to say that it can't be simplified in other ways, but I just kind of like this way in terms of better understanding it without having to get too caught up in the details. All right, so in this example, we're going to find the equation of the plane passing through these 3 points, okay? What we have here essentially is we've got our plane, we've got 3 different points embedded in it, and we need to come up with the equation. Well, the equation of a plane, you need a point and you need a normal. So you can pick any one of these points, but then you also need the normal vector. So to construct that normal vector, what we're going to do is we're going to construct 2 different vectors here and here, and then cross them, and we'll get that normal vector that we're looking for. So it doesn't matter the combination that you pick. I did PQ, vector PQ, and so for vector PQ, again, we're going to subtract the components. We'll get a -1, -1, -2, and then QR as well. So that's going to be a -3, 2, 3. And again, to come up with those, we would do like a -1 minus a 2. 3 minus a 1, and 2 minus a minus 1. That's going to give us that there. All right, so those two vectors now will need to be crossed. So if I take PQ and cross it with QR, that's going to be IJK. And we'll take -1, -1, -2, -3, 2, 3. And remember, the order in which this is done won't matter. If I interchange those, the only difference would be one would come out positive, one would come out negative, and the direction might be different, but it would still be perpendicular, would just point down, so the direction doesn't matter. Same thing here. If you did PR, for example, and got a different vector, you would end up with a scalar multiple of whatever it is we come up with. So there are many different options here, and as how to proceed. So if you go ahead and you cross these now, you end up with the vector 1, 9, -5. So we've got our point, pick any one of them. I'll just go ahead and pick this one out of convenience. And we've got our normal vector. So as I put this together, my A value would be 1. Again, this is A, this is B, this is Z, this is X naught, Y naught, and Z naught. So that's going to be a 1 times X minus 3 plus a 9 times Y minus 2 minus a 5 times a Z minus 1. Set that equal to 0, and there would be our answer in terms of the equation of a plane passing through those points. Depending on what the homework suggests, you could simplify that down to any number of ways. All right, so for this one, now we're going to be looking for the line of intersection. So since we're searching for a line of intersection, we need a point and we need a direction vector. Those are going to be the two things that we're searching for. Now, when it comes to a point, again, there's a variety of ways to do this. I generally, and I think it's a pretty common approach, will take these two things. Again, we're just trying to find a point of intersection. So I'm going to let Z equal 0. Maybe I'll do that in a different color. We'll let Z equal 0. And if I do that, that gives me a 2x minus y equals 5 and an x plus y minus, equals 1. So again, all I've done there is let my Z equal 0. So 2x minus y equals 5, x plus y equals 1. Now I've got a system of equations that I could solve very quickly. If I solve this, and again, when I say quickly, it's set up nicely. That's going to just give us an a 3x equals 6 and an x equals 2. If x equals 2, I'll plug that back in somewhere, and that'll tell me my y is going to equal -1. Therefore, I found a point of intersection of 2, -1, and my z coordinate to start with 0. So you can do that in any way you'd like, but there's our point of intersection. Now, the direction vector is going to be actually pretty interesting because we're given two planes. We know that the vector 2, -1, 1, 1, 1, -1, those are going to be normal to the planes. So let's say that this guy right here will have our normal vector 1 of 2, -1, 1, and this will have our normal vector 2 of 1, 1, -1. Now, I'm going to make a very poor attempt here to draw this, but this is hopefully the way that you can start to visualize it a little bit. So I'm going to take these planes, okay, and again, this is very poorly done. I understand that. So there's one, and then here's the other one right here. Now, these vectors that I came up with, N1 and N2, are going to do this. So here's, let's just say that's perpendicular there, and that's going to be N1. This one comes out of here, and that's going to be perpendicular, so we'll call that N2. Now, we're searching for the line of intersection of planes. Well, that line that I'm talking about is this guy right here. And so if we view it head on, this is very difficult to do without seeing you guys. If we view it head on, you're just looking at a point. That point's going to come out of the screen and it's going to go into the screen, okay? Which means our direction vector would look like this as well. And if you can't see what I'm doing, it's going to be this guy right here coming out of the screen at us. So this direction vector coming out of the screen at us and this direction vector coming out of the screen at us, those are going to be parallel, and that's what I'm going to need for my direction vector of my line. So if I look at this vector and this vector, when I cross those, that's going to give me the vector that's perpendicular to both, or the one that's coming out of the screen at us. So for the direction vector, I'm going to take N1 and cross it with N2. So we've got our I, our J, and our K. We've got our vectors of 2, -1, 1, 1, 1, -1. And when we cross this, we get the vector 0, 3, 3. So that guy there, that's going to be now our direction vector. So when we put together our format for equation of a line, x is going to be 2 plus 0t, y is going to be -1 plus 3t, and z is going to be 0 plus 3t. So the 2, -1, 0, 2, -1, 0, and then 0, 3, 3, 0, 3, 3. So the format holds. And so this one's a little harder to see, but I still think it's manageable when you draw it out in a simple way and understand that the vector or the line that's coming out of here, coming out at us, is going to be parallel to the vector coming out of here from the cross product of N1, N2. All right, the last thing I'll mention is angle between two planes. And again, I'm starting with a very poor picture of two planes, and we want to talk about the angle between them. So to study this, to no surprise really, we're going to take a look at the normal vectors coming out of here. So maybe we'll call this one N1 and this one N2. And so the fact that these are perpendicular to the planes they come out of is going to then allow us to use those with our quote-unquote dot product formula from before to figure out the angle between these planes, angle theta. So it's going to be a very similar setup, very similar idea, where we now just use the N1 and the N2 as the vectors. So cosine theta equals N1 dot N2 divided by the magnitude of N1 and the magnitude of N2. So really nothing too surprising there or shocking. The book does have a picture in there. It's probably better than mine. I'd recommend you take a look at it, page 735. But overall, the concept is very, very intuitive.